Hi, we're Team 32, and our project is to make an optical emission probe for high enthalpy plasmas. Our client is Jason Myers, a member of the research faculty here at the UVM Plasma Test and Diagnostics Laboratory.
My name's Colin Freiheit.
I'm Andrew Morin.
I'm Alex Harrington.
And I'm Jeff Shinley. The Plasma Test and Diagnostics Laboratory has a 30 kilowatt inductively coupled plasma torch, which is used with various gases to simulate atmospheric reentry. Our team was asked to design a probe which can take emission measurements at various radial locations in the plasma jet.
Previous emission measurements were taken through a window with the optical elements located outside of the torch.
One of the biggest requirements was that the probe had to be able to withstand the plasma environment, which can get up to 8,000 degrees Kelvin. In order for the plasma chamber to function, the probe had to maintain a vacuum seal inside of the chamber while it was inserted. The client also asked that the probe be able to be translated in increments of 1 millimeter, and that it be easily connected to the lab's existing spectroscopy equipment.
We played around with a number of different vacuum feed-through designs and water cooling schematics. We ended up deciding that a simple lock nut seal would be used for our design, as the more complex automated methods for translation were deemed too costly. This seal seemed like a good starting point for the design as well, and we knew the client could always adapt a more complex automated feed-through in the future if he wanted. The concentric water cooling system was also chosen. We wanted the core of the probe to be easily disassembled and removable. As a result, the cap and the butt of the probe were designed to be threaded, and O-rings were incorporated in order to retain the vacuum seal. We wanted the core of the probe to house the fiber and feature a lens which collimates light into the probe. The back of our probe needed an easy way to connect to spectrometers that we already have in the lab. We chose to use an SMA connector on the core of our probe so that this was possible.
We relied heavily on CAD software to conceptualize our design. This allowed us to easily visualize and integrate the standard copper components and optical elements that we planned to purchase with the unique pieces that we would have to manufacture. Some rudimentary thermal analyses were used to get a rough idea of the cooling capacities of the probe, and the probe was analyzed to ensure it could withstand the pressure of a vacuum. An extensive analysis of the O-rings was performed, as the probe leaking in any capacity was unacceptable. The most critical element of our design ended up being the cap of the probe, which has a very complex shape that was difficult to manufacture. We worked with IMF to manufacture this component. While the creation of this component was incredibly expensive for us, the finished cap performed how we hoped it would. Initially, we had difficulties integrating the fiber optics into the probe. In order to terminate a fiber optic so that it can connect with other fiber optic cables, there's a complex process required that involves using epoxy, a fiber cutter, and polishing tools. After painstakingly trimming and polishing the fiber we had purchased, we found that it did not transmit any light. In the end, we had to purchase another thicker cable and restart the whole process, as well as order new polishing materials. Thankfully, with the thicker optical fiber, light was transmitted through the probe, as we hoped it would.
At this point, we have a fully operational probe which is able to transmit light from the plasma to the outside of the chamber. The probe was also able to cool the lens enough to keep it within its operating temperature range. One specification that we were not able to satisfy was the level of collimation of the light going into the probe. We wanted this light to come in at an angle of less than 5 degrees. We were not able to satisfy this, but this isn't really a critical specification, and improvements can be made in future iterations of the product.
The lab will begin using the probe to collect data in the future, and our client says that he would like to build an attachment that allows the probe to look down into the plasma.